So, third installment then, and second example for you. So, let's consider the Moon orbiting Earth, because that's what it does. It does that every 27.3 days. So let's look at how many seconds there are in 27.3 days. At a radius of 400,000 kilometers, which of course we'll have to work into meters. Let's calculate the centripetal acceleration of the Moon around the Earth. So, the period, which is 27.3 days times 24 hours times 60 minutes in an hour times 60 seconds in a minute, and the radius, which is 400,000, oh, my apologies. I was right, 400,000, I've got 40 million kilometers, 40,000 kilometers. So there's too many zeros in there, 40,000 kilometers. 40,000 kilometers, 400 million meters. So you say, well, how are we going to do this? We don't know the mass of the Earth. We don't know the mass of the Moon. Well, we don't need that. We say omega is 2 pi over t, where t is 2 pi over omega. So t is 2 pi over omega. So we've got our 27.3 by 2 by 24 by 60 plus 60 equals 2 pi divided by omega, which gives us omega equal to 2 pi divided by all of that. And we know that A equals v squared over r. And of course, also v equals r omega. So we have A equals r omega squared. So equals 4 times 10 to the, what is it, 368 is the radius of the orbit, times omega squared, which is all of that, squared, So if we work that out, we've got 7.3 times 24 times 60 times 60. And we are dividing 400 million by that. We had to square it first, as I didn't do. 27.3 times 24 times 60 times 60 times itself, whatever that, times 400 million. That gives us 2.8 times 10 to the minus 3, which I'm sure you got there faster than me, because I made a few mistakes with my calculator there. So there we have 2.8 times 10 to the minus 3 meters per second squared. So that is the centripetal acceleration of the moon around the Earth. So there's example 2 for you. Now let's do example 3. And this is going to be a conical pendulum. You say, what is a conical pendulum? Let me show you what I mean by a conical pendulum. Well, that didn't work. Let's try again. There we go. So this is my pendulum, my string. Here is the weight of the bob on the string, but instead of swinging backwards and forwards, it's performing a circle. So here we have the outline of the path taken by the bob as the pendulum swings. So the pendulum is coming around like this. So that's a conical pendulum. Okay. So what we have is a mass m kilograms on a string, tension S newtons. I'm going to call it S because we don't want to confuse T the period and T the tension, so we're going to call it S for now. And so our conical pendulum is performing a circle. And again, let's call this a horizontal circle just to be really clear. That's what we're doing. Or let's say derive an expression. For the acceleration of a bob. So what we have here, of course, is a situation where we need to resolve the tension S into two components. If we resolve vertically and horizontally, that seems to make sense. So we resolve horizontally. Well, if you think about this, if you were to draw the line of action of the weight vertically up, you'd have two parallel lines, this one, and from your maths geometry you would know that this angle and the angle in here are the same. So you're resolving this force going in this direction horizontally, so you're rotating away from the angle here, and so you're going to have S sine theta. And if you resolve it vertically, you're going to have S cos theta. So where does that get us? Well, S sine theta is the only force horizontally, whereas vertically, S cos theta will equal mg. I've got mg down here, I've got S cos theta up here. Those two forces will be equal. There is no acceleration in the vertical plane. The bulb is not accelerating up or down, it is accelerating in the horizontal plane. So these two forces are equal, so there is no resultant force vertically, but there is a resultant force horizontally. Which is S sine theta. Which therefore equals mv squared over r. So our acceleration then would be S sine theta over m. And let's just change that back to aerial again. So there we have our expression for the acceleration of our conical pendulum.